Okay, we're recording. So, yeah, last time we were talking about this question here. This is kind of a foot in the door, trying to come up with something that might sort of seem reasonable in some sense to maybe be a first attempt at a multivariable integral. So we think to ourselves, hey, area under the curve was kind of the motivating example anyway of single variable integrals. How about we try volume under the surface? Now again, very importantly, that this surface be a graph, right? Just like when you're talking about area under a curve, that curve has to be the graph of the function in question. So given that we have a graph, how would we find the volume under this surface sitting over a certain rectangle? And what we argued last time was that if you kind of think of this as sort of a loaf of bread of sorts, then the volume of the whole loaf is the sum of the volumes of the slices of bread. Stands to reason, right? Reasonable argument. The question was how to compute the volume of each individual slice, the sticking point of which was how do I find that cross-sectional area? And what we argued last time was that cross-sectional area itself is another single variable integral. It's a single variable integral where we're going kind of in the x direction. And so altogether then, putting together the pieces, let's see here. So we first argued that we want to do an integral in the y direction, the slices of which would look something like that. And then to understand those better, each of those we have to understand as being an integral in the x direction, the slices of which would look something like that. And putting this all together is how we ended up with this thing called an iterated integral to compute the volume under a graph. Iterated integral. It's an integral inside of another integral. And I think the very last thing we probably mentioned, something that I mentioned very close to the end of this discussion, is to keep in mind that when you're talking about the inside integral, don't forget what you're doing. Don't forget what the context is of this single variable integral. X is going from A to B, the purpose of which is to help me understand this area. That area having been defined by having chosen some value of y. Right? I can only talk about cross-sectional area if I have in fact fixed, set as a constant, some value of y at which to even talk about the slice in the first place. Right? So, very importantly then, while you're talking about this inside integral, the outside variable is to be treated as a constant because it is a constant. Right? So, really important little detail to keep in mind. And with that in mind, we move along to this example. And let's see here. Here we have, you'll notice, a graph of some function. It has, some shape. Something like that, some surface kind of like that. We're looking at the part sitting over this rectangle, and the rectangle is given with a notation that you may or may not have seen before. So let me momentarily pause the question to talk about what this notation means. This notation, 0, 1, cross 1, 2. This is not a cross product. This is just a different use of that little kind of cross symbol. This indicates a rectangle where the understanding is that the first interval is telling you the corresponding interval on the first axis, namely the x-axis, and then the second interval is telling you the corresponding interval on the second, in this case the y-axis. So I think you'll see from the picture here that with the understanding that this is the shadow on the x-axis and that's the shadow on the y-axis, then this is the rectangle that we're talking about. It's a very convenient, compact notation to help us describe an entire rectangle in the xy plane. Okay, so that's it. The question is find the volume under the graph. We've already argued that a volume is this iterated integral. just lifting exactly from what we saw earlier on this page. And now it's time to plug and chug. So now there is one sticky wicket on this. Well, before I get to the sticky wicket, let me zoom in a little bit and point out keep in mind this is the range of values of x over this rectangle, and notice that is also my range of values of x for my x integral. Right? Nice little pattern there. Likewise, the range of values for y on my rectangle, well, that determines the range of values of y for my y integral. Okay. Again, just like above. Okay, so where's the sticky wicket? The sticky wicket comes when you do the integrating, aka the anti-differentiating, I would rather call it. So no surprises in doing this dx integral, x being the variable. This expression of x integrates exactly the way you would think it does. 1/3 x cubed, no surprises there. Right? Exactly what you would think. The sticky, questionable, dangerous part is what to do with the y squared. This is where a lot of students will mess up. A lot of students will remember reflexively from single variable calculus class, oh yeah, power rule, so this should be like 1/3 y cubed or something. That's absolutely wrong. Has complete, it would be a complete misunderstanding of what's going on here. So here's why. As we just discussed, the outside variable, y, has to be a constant. For this inside integral to even be something we can talk about. So if y is a constant, I have to treat it as a constant, and when you have an expression of a constant, that too is a constant. And the antiderivative of a constant is constant times the variable. Don't forget the variable is x. So same constant times x. So how are we doing on this anti-differentiation on the inside? Does everybody see how that works? Real dangerous little landmine. Please be sure not to step on that landmine. No 1/3 y cubes in a situation like this. Yeah.
Can you explain why again? Like we're treating y as a constant.
Yeah. Well, that's because of this business up here. Let's see here to get over here. So this integral represents this area. This area is only, in order to know which area we're talking about, I have to settle on what x is, what y is, excuse me. Okay. All right, so pretty much everything else is exactly what you would think. It's just single variable calculus followed by more single variable calculus. There are, after all, 2 single variable integrals to be done. I have a little superstition that I like to share. I've probably done this in the distant past myself, where these values for x, they go over here, and you have 0 to 1, 0 to 1, and you start plugging those values in. And the thing about it is, if you don't write x equals, then what can happen, it's easy to lose track, is you can take, for example, this value 1, and you plug it in for the variable, and then you plug it in for the variable, and then you forget. It's easy to forget. And accidentally also plug it in for that y, which also kind of looks like a variable, right? From the last part of the alphabet. It's easy to forget. So my little hack, if you want to call it that, is instead of writing down my x bounds as just numbers, I like to include specifically x equals 1 and x equals 0. That's my little visual reminder to keep me from doing something silly, right? You don't have to do that. It's entirely optional. I think it's a really good idea. I strongly encourage you to do it, just to avoid the oopses. Okay. All right, how are we doing? Everybody on board? Details for y'all to read on your own, of course. Okay. So now you can slice in the other direction. Just going back real quick, let me remind you, we had this loaf of bread, as it were, and we decided to slice it one direction, right? I decided to slice with Y going that direction, and so that's what my slices look like. But you could, it's just a piece of bread, right? You could slice in the other direction, thus giving you cross sections that look like this. Little pieces of volume, little slices of bread that look like that. And then you can compute the volume of one of these by computing its cross-sectional area. As you then go in the Y direction, it's like the X is doing what the Y was doing, and the Y is doing what the X was doing. You can draw the corresponding pictures. Think about the different roles that the different variables are playing at the different stages in the calculation. You'll come up with a different iterated integral. And here's what you'll get, as it turns out. I think this is a really healthy exercise. This is the one that we walked through together. And if you were to slice in the other order, you would get this. Please give this a shot. Again, you don't have to, but I think this would be a really good idea. Give this a try and confirm that you get the follow through the details and make sure you notice the details. A couple of things to point out. Not only is your formerly outside variable now on the inside, not only is your formerly inside variable now on the outside, but likewise the bounds switched too. What had been the inside bounds are now the outside bounds, and what had been the outside bounds are now the inside bounds. The point to notice, easiest way to think about it, I think, is of course they go together. When we say C to D on the outside, we're talking about a range of values for that variable. It remains that variable, even if you slice in the other order. So when you switch differentials, like so, also switch the bounds at the same time. Is everybody on board? Okay. All right. Now, we have only to this moment talked about rectangular domains. I do want to get ahead of a problem, though. We are very soon going to be talking about non-rectangular domains, probably on Monday. I doubt we'll get to it today, but possible. Anyway, when you have non-rectangular domains, this business right here with the switching and the bounds just kind of do what the differentials do. Not anymore. This is only for rectangular domains. Once we get to non-rectangular domains, things get more complicated and it just doesn't work. Be careful about that. Okay. All right, now here's some bad news. Going back to, by the way, where we had been, looking at this question here. Why did we ask this question? It seemed like a reasonable first step. We want to kind of try to copycat what we did in single variable calculus and come up with sort of a multivariable version. And volume under a graph seems like a reasonable place to start. Area under a curve being very analogous. Okay, well, here's the thing. The tool that we use to compute area under a curve happened to be exactly the tool that we also could use to compute a bunch of other stuff. We computed, answers to questions like if you have an interval on the x-axis, no graph, no curve, just an interval on the x-axis. And if there's mass distributed across that interval, with more over here, maybe less in the middle, and then more on the side, whatever, right? You want to compute the total amount of mass, that too could be computed with the exact same single variable integral. So you would be forgiven for hoping that this exact same tool that we use to compute volume under a graph would also allow us a perfectly reasonable strategy for making sense out of how to compute other stuff. Like, what if I have, instead of volume under a graph, maybe I just have mass distributed across the rectangle. Purely two-dimensional, no graph, no z, just mass distributed across a rectangle. Maybe I can compute that mass with this same thing. And I'm sorry to report, that doesn't make sense. And this is my argument as to why it doesn't make sense. Now I want to distinguish, be very careful to distinguish here. I'm not saying that this won't give you the right answer. It turns out, we'll see later today, that this would give you the right answer. But again, that's not our goal. That's not what we do here. Our purpose in this course is not to get answers. Our purpose is to understand reasoning and arguments. And the argument that we have at our disposal right now to make the claim that this iterated integral would compute mass doesn't make any sense. Let me walk you through why. Let's look at what we have right here. When we were computing volume under a graph, this being looking at a graph, that was our height. dx was kind of a length, if you will. And yeah, cool, no problem. Height times length, pre-existing geometric idea that I understand. That's area. We got lucky. It happened to be that the thing that was the integrand here and the thing that was our differential, the multiplying that we did happened to produce something that we already know. Area and area. We know a lot about area. We don't know just how to compute it. We know how it behaves. Area is an accumulating quantity, by which I mean the whole is the sum of the parts. If you take an area and you slice it up, total original area is the sum of those pieces of area. It's what I call an accumulating quantity. Well, that's really nice. That's how we made the argument that we could compute that whole with, in fact, this integral, right? Because we know area has this feature, that the whole is the sum of the parts. Okay, now, wishful thinking. Let's try to do the same thing over here. Let's look at, the integral we would have written down. With hope in our minds that maybe this will compute mass for us. And we look at the exact same analogous thing, and our integrand here, mass per unit area, telling us how mass is distributed across our rectangle, times length. And what do we get here all together? What is mass per unit area times length? And the short answer is, I don't know. That's not a thing. Mass per unit area is intended to be understood as something you multiply by area to conclude mass. Mass per unit area, the only thing we know about mass per unit area is what happens when you multiply it by area. That's not what I'm doing here. So what is this thing? Well, you could make a case, I suppose. You could try to make a case that it's mass per unit width. Yeah, mass per unit width. Well, what's that? Does that accumulate? Is the whole the sum of the parts? Are you sure? You see, we have a problem, right? The reasoning, there's some sticky wickets in there. And now, as it turns out, yeah, you can go to some trouble and make sense out of these things. But there's work to be done there, and we don't want to have to go through a sophisticated and subtle argument to understand a new, unnatural physical quantity every single time we want to compute something with an integral. And so I'm going to say we're dead in the water here, that this is not something we already understand. We don't know if it accumulates, and I just can't just go around claiming that I can add up pieces and that the whole is the sum of the parts, because I don't know that about this expression. Okay, so this argument does not work as an argument. Okay. Is everybody okay with that? Everybody see the problem? Okay. All right, so we're going to fix it. We're going to fix it by creating a new kind of expression. The new kind of expression is going to be based on an old kind of expression. I need to remind y'all, just to make sure we're all on the same page here, what a single variable integral is. As I try to define something called a double integral, It's going to be modeled on single variable integrals, and we want to make sure we start off with the right understanding of what a single variable integral is. It's very commonly misunderstood. A lot of people think that an integral is defined as f of b minus f of a. No, it is not. That's a theorem, not a definition. Very importantly so. A lot of people think it's defined as area under the curve, specifically a graph, so area under a graph. Also, importantly, not true. That's an application, not a definition, and not a particularly useful application, frankly. This whole idea about understanding integrals as areas is very, very oversold. What an integral is a Riemann sum. As far as we're concerned in this class, it's a Riemann sum, with certain specifics being, understood. So now, is this ivory tower mathematicians enjoying writing down difficult formalities? No, this is actually really important to applications. It's really a big deal, a very underappreciated point. So let me try to argue why this is important, and I'm going to start by pretending we don't have Riemann sums. Let's just kind of forget about Riemann sums. Let's pretend that we try to argue that integrals are just area under a curve, area under a graph, sure, and that the fundamental theorem of calculus is a tool for computing those areas. Let's just say. All right. Fine. I want to compute the amount of mass, distribute over an interval. Like the old classical single variable calculus problem. You got an interval from A to B. It's a one-dimensional question. There is no y-axis, only the x-axis. Density is known. Mass per unit length is understood as what it is across that interval. Can I argue that mass on a one-dimensional interval is somehow equal to an area? And I say no. I don't. How does that argument work? The mass is distributed across a length, for one thing, so what's area got to do with it? I don't think this argument holds water. It doesn't make any sense. This is a nasty little point, right? I mean, a lot of people have become kind of accustomed. But we did it a million times in high school calculus class. That doesn't make it a valid argument. And in fact, what you did in a high school calculus class was to argue, depending on how rigorous you were, one way or another, that mass is a Riemann sum. Now, you may have, after arguing that it was a Riemann sum, then understood that Riemann sum as an area. Yeah, maybe, sure, fine. That's a reasonable thing, I suppose. But importantly, you have to have the idea of a Riemann sum. You have to take that interval and chop it up into little pieces. And then that resulting Riemann sum, yes, you could, I suppose, interpret as an area. So if you take Riemann sums out of the story, then you're dead in the water. So very importantly, integrals are Riemann sums. And this makes all these problems go away. You want to compute mass? Yeah, great. That's an accumulating quantity. The whole is the sum of the parts. Oh, you want to compute the population of bacteria, blah, blah, blah. Great. The whole is the sum of the parts. Oh, you want to compute a probability that a certain thing happens? Well, you break that down into cases. And the whole is the sum of the parts in the cases. All of these turn questions, application questions, into Riemann sums. So this is a really big deal. Very important to make sure you understand that integrals are Riemann sums. They are the algebraic manifestation of a strategy. The strategy being to take a whole, chop it up into little pieces, and argue that the whole is the sum of the parts. As I like to call it, chop it up, add it up. All right, so enough of that. Let's move along. And what would be the sort of multivariable version of this? In The multivariable version goes like so. Rather than take a one-dimensional interval and talk about how to chop that up, and then answer questions on individual pieces and add up over all the pieces, which of course gives rise to a Riemann sum, as y'all saw back in whenever you saw single variable calculus. Well, maybe instead of a one-dimensional interval, maybe we now have a two-dimensional rectangle. And we're going to talk about now how to take this two-dimensional rectangle, how to chop it up into a bunch of little pieces, argue that the question at hand, whatever it might be, is easy on each piece, and then add up over all of those pieces. So it's we're going to end up with a kind of vaguely similar looking expression there, intended to kind of model what happened over here. It's just that it's a two-dimensional thing that we're adding up over instead of a one-dimensional thing. Big picture only. Are y'all okay with the big picture strategy? Yeah. Details to follow. Okay. All right. So let's talk about these little details. We're going to slice it up by slicing vertically like so or so. And we're going to slice it up horizontally kind of like this. Yeah, worked out pretty well. So I started off with this great big huge rectangle that I've chopped it up now in two different directions. The result being that I've chopped it up into a bunch of little bitty areas. And on little bitty areas, some questions are really easy to answer. So for example, let's suppose we are interested in computing the grand total mass distributed over this rectangle. So mass now understood as distributed not over a length. We're not going to talk about mass per unit length along one direction. We're going to talk about mass per unit area across a rectangle. This was the sticking point. This is why it didn't work when we were dealing with iterated integrals, because we had mass per unit area and we weren't multiplying by area. But now, having chopped up the rectangle into little pieces of area, if I want to know how much mass is in that little sub-rectangle, well, it's mass per unit area times area. That's mass. No problem. No funny business. Just a little piece of mass. And if you want to add that up over the entirety to get the total mass, yeah, cool, fine. Add it up over all those pieces. All good. No problem. There's always going to be round-off errors. You remember that the purpose of this limit in a single variable Riemann sum, the purpose of the limit is to deal with the fact that there's little round-off errors, and we want to make all that go away. And for sufficiently nice functions, in the limit as n goes to infinity, all that round-off error goes away and all is good. I'm going to assert the same thing here, that if you have a sufficiently nice function as your integrand, then in the limit, all your little round-off errors go away and everything's good. So, now, let's consider a different kind of question. What if we're not computing mass anymore? What if we're computing the amount of population? We're computing the population of Wyoming or Colorado, right? All right, no problem. Total population is the sum of the parts. Holds the sum of the parts within any given little sort of county-like little rectangular region. Population per unit area times area gives me population. No problem, no funny business. The whole population is the sum of the little pieces of population. It's fine. It works just as well for computing population as it does for computing mass. It works just as well for computing anything that you can view as accumulating over that rectangle. Any sort of accumulating quantity. So, roughly speaking, I'm going to say that with this strategy in mind, this expression right here is super useful. This is the whole of the sum of the parts formula for any sort of accumulating quantity that accumulates over an area. And things that are that useful deserve a name and a notation. So this thing here, we're going to call it a double integral. We're going to use this notation. I claim it's fine and makes sense as is for any continuous function. There's, by the way, a whole field of mathematics that's dedicated to under what circumstances, how nice does your function have to be for this expression to make sense, and how do you have to adapt this expression? What if the function's not continuous? What if it's not quite continuous, but almost in some sense? Does this still work? There's a whole bunny hole that we're not going to go down there. It's not the purpose of this class. It's beautiful mathematics, but it's not what we're here for. So I want to point out that what the book does is a very nice step down that bunny hole. That is not what we're here for. And so y'all are welcome to ignore all the books talk about irregular partitions and arbitrary test points and et cetera, et cetera. That's really, really important for stuff that we are not going to deal with or care about at all. Everybody cool with that? By the way, if you do want to see what the deal is with this, take Math219. It's a beautiful course. And there's a really good answer as to why we need stuff like this. And it's just classical. It's this math that we're going to skip over is to math as Mozart is to music. It's classic. It's wonderful. It's a period piece, right? But it's wonderful stuff. Okay. All righty. So, armed with our new tool, let's revisit an old question. Volume under a graph. Right, so we have this graph surface. We have a rectangular domain given down here in the xy plane. And I want to compute the volume sitting under the graph and over the rectangle. And how would you compute that volume? And again, slice of bread, et cetera, et cetera. A double integral says, let's not view this as a sum of a bunch of slices of bread. The double integral says this is a bunch of French fries. Right? What's the total volume of our biggie fries thought of as a sum of the volumes of the individual fries? Right? So the individual fries, easy, no problem. Height times area of the base. If you like, you could view this as volume per unit area times area. Nice way to think about it. Accumulating quantity per unit size times size gives you the accumulating quantity called volume. And then you observe that that's literally exactly character for character our Riemann sum that we just got through being happy about and giving this new notation, calling it a double integral. Are we good? Okay. All right. Now, complaint. When we were doing this with iterated integrals, back to here, right? And we argued that volume was this iterated integral. This is something I could actually compute because this single variable integral on the inside, fundamental theorem of calculus, bam, awesome. Then having done that, we find ourselves with a single variable integral. Again, totally no problem. Fundamental theorem of calculus crushes it. So 2 applications of the fundamental theorem of calculus, and I know how to compute iterated integrals. By contrast, now that I've turned my question of volume into a double integral, do we have any tools for computing double integrals? No, we don't. So, pretty valid complaint that really the iterated integral argument was kind of a better one at this stage. Okay, so here's how we can kind of turn that around, though. Don't forget, we've already argued that volume... Oh, whoopsie, I missed wrong one. We've already argued that volume can be computed with either one of these iterated integrals. We have now shown that that exact same volume could be computed with a double integral. So in fact, really the big takeaway of this example up here, don't think of this example up here as establishing that we can compute volume with a new formula. It's not really the point. That wasn't my motivation in doing this example. My motivation was to point out that that shows that I can compute double integrals with iterated integrals. And now we're cooking. Okay, let's put it all together. I know we've talked about a bunch of different constructions and relationships. Here's a sort of a road map for all the stuff that we've talked about. The very first thing we did, again, was this right here. We considered the narrow question of how to compute volume under a graph. We came up with iterated integrals. Fundamental theorem times 2 gives us an answer. That's what we did last time. We've just gotten through arguing that you could also compute the volume with a double integral, thus pointing out that I can compute double integrals with iterated integrals. So now I've got all these connections. And now let's ask the important question as far as, anyone in a practical major, engineering, physics, something like that, right? The questions that y'all are really interested in, how do I compute, forget geometry, forget math, I want to compute stuff. Mass, population, work, whatever. There's a million applications out there, endless applications. How do I compute these? And I've already argued, you can't just go around claiming that two-dimensional problems have three-dimensional answers. That doesn't hold water. That just doesn't make sense as an argument. Why did I color that in blue? That doesn't make any sense. You can't just claim that they're volume. Says who? You can't write them down as iterated integrals either. The units don't work out. Right? We already tried this with trying to make sense out of mass. You can't write mass as an iterated integral. You've got mass per unit area that you're going to need to multiply by length. And we don't know what that is. So that doesn't work either. But we have exactly one reasonable path that we can follow. And you can see, of course, the path right here. The path is like this. Step 1, whatever your application is. Oh, whoopsie. Colors. Step 1, turn your application, whatever it is, into a Riemann sum, aka double integral. Argue that the whole is the sum of the parts, in other words. Sure. Cool. No problem. Double integrals are designed to make sense for any sort of accumulating quantity. Step 2, cite the theorem that we just wrote down. Double integrals can always be computed with iterated integrals. Thank you, volume. That was a nice little result for us. That important little step in the process that we argued by way of the volume application that, in fact, in practice, most of the time, we actually don't really care about. Very rarely what we actually need to know in practice. And then step 3, with an iterated integral, of course, crank it out with the fundamental theorem. Times 2, of course. And there you go, you get your answer. Everybody see the argument there? Okay, let's see one. Okay. All right. Back to the computing of mass. Here's where we crashed and burned with iterated integrals. This density right here is mass per unit area. Iterated integrals would have you write down mass per unit area times length. Again, not a thing. I don't know how do you deal with that? That doesn't make any sense. So what we're going to do instead is argue first that mass is an accumulating quantity. The whole is the sum of the parts. Of course it is. It's mass, right? If you could make mass disappear or appear by subdividing it, there'd be all sorts of applications of that little trick, wouldn't there? Right? That'd be really not true, though. The whole is equal to the sum of the parts. It's accumulating quantity. On any given piece, mass is mass per unit area times area. Again, that's a perfect fit. That's what mass per unit area was made for. Mass per unit area was made to be multiplied by area, to be interpreted then as mass. Nothing to it. Then we recognize that, wow, look at that. That's exactly the definition of a double integral. So now all of this together I'm going to call step 1. I've expanded this into sort of 3 steps just for illustration purposes. I wanted everyone to see what's going on inside of this claim that applications can be turned into double integrals. And in practice, on an exam or something, you don't need to give me all these intermediate steps. It's perfectly fine to just go mass, double integral of density. No problem. All good. Everybody good so far? Now, before we go on to step 2, I'll point out the alternative notation. I mean, look, you can see this coming at the very end. This is just going to turn into that. This is going to be, I mean, you know, this is going to turn into that. The notation, the integral notation and the Riemann sum notation, I mean, they track pretty directly, and that's really what integral notation's for in the first place. So as a shorthand convenience, and this is convenient and also very standard, you can just write this with the integral shorthand throughout the process. Perfectly fine. Very standard. It's to be fair, a little bit of an abuse, I guess, but very standard. Practically everyone does it. So when you see, and you're going to see me do this a lot, by the way, when you see this written down, don't look for an M-axis. That's not what that is, right? This is just a shorthand for this, which is literally just saying I'm adding up little pieces of mass to get the whole mass. It's just a shorthand for a Riemann sum, in other words. All right, so I like that little notational shorthand. Anyway, step 1, mass is a double integral. Step 2, double integral is an iterated integral. Step 3, I can compute the iterated integral with the fundamental theorem of calculus to get an answer. Just like on the previous page. Right? Step 1, turn it into a double integral. Step 2, I forgot the colors I used. Step 2, turn the double integral into an iterated integral. Step 3, punch it up with the fundamental theorem. There we go. Okay, so there's our 3-step process. Everybody all right? Do keep in mind, this is an important point from a grading standpoint. That again, this is not about answers. This is about reasoning. Reasoning's important, and you can see we've gone to a lot of trouble here, defining a whole new thing called a double integral to get around the fact that this right here is a bunch of nonsense. Right? Now it gets us to the right iterated integral, but it doesn't make sense as an argument. Right? So we went to a lot of trouble then to point out that as bad reasoning. So please don't just take your application and immediately write your iterated integral, because taking an application and immediately writing it down as an iterated integral is indistinguishable from not understanding the need for double integrals in the first place. And that's a big problem, right? Again, in terms of the reasoning. And again, this is a class about reasoning. So you gotta give me the double integral so that I can tell that you're not doing this argument right here. Right? And so in the specifics, in the particulars, if this thing will expand, there we go. If you were to take mass and just immediately write it as this. Okay, look, I recognize, I know, in fact, you might have in your head, you might have been thinking, okay, well, yeah, math, it's a double integral, but look, why do I have to write down the double integral? I'm just going to rewrite the double as an iterated. Why don't I just write it as the iterated? Save yourself those 10 seconds, right, of writing down the double integral. I get the temptation, but you got to remember, this is indistinguishable from someone who doesn't understand why double integrals matter. So please make sure to distinguish yourself from someone who doesn't understand this huge point that we've spent the last 30 minutes talking about. So you got to give me that. That's really important. Pausing to make sure we're all good on this. Everybody happy? Feel free. Question? All right. Okay. So I'm going to show you one last example, and then we'll call it a day. I'm just going to elaborate on this idea that double integral notation is a convenient shorthand. That's this business up here, writing it like this instead of this. Right, the double integral shorthand. It's just a little bit more compact, a little bit more convenient. It's just a shorthand. So, for example, and here's just another example of how that's really useful. Let's consider this application where we're going to build a kind of a wall of sorts. I came up with this question when my wife and I were buying a house, and there was this facade. The front facade is kind of this stone kind of thing. It's real cool looking, and it's made out of stone. Stone's heavy, and I was looking at this big stack of stones, thinking somebody's going to have to pick those up off the ground and lift them up to actually fairly high. And wow, that seems like a lot of trouble, a lot of effort. And it occurred to me, hey, this is a nice little application problem. So how much work does it take to lift the stones from ground level up to where they need to be in the wall? All right, so the very first observation I make, and this is my whole as the sum of the parts, doff of the cap to this simple point, work is an accumulating quantity. The grand total amount of work that it takes to place all of these stones is the sum of the amounts of work that it takes to place each individual stone. So, okay, fine. Next question. How much work does it take to pick up a stone off the ground and place it right there? How much work does that take? Well, work is force times distance. So total amount of work for that one stone, well, I need to know the distance, namely how high did I lift it, namely what's the altitude of where it needs to be, that's y. And then I multiply by the weight. How much does that stone weigh? And this is what we call a differential amount of weight because we're looking at the amount of weight on just one little teeny tiny little piece. So all that is work equals force times distance using integral shorthand. Weight is weight per unit area times area. This is using weight, not mass, by the way. So pounds, for example, is a unit of is an example of weight. Weight is a force, not to be confused with mass, which you have to multiply by acceleration to get force. We don't need to deal with that. We're just going to go straight in terms of pounds per unit area times area to give me pounds. All forces. Okay. And then grand total, then this is my step one. I've turned a question into a double integral. And I feel like the integral shorthand is just a handy way to kind of work up exactly what my double integral needs to be. At which point, it's all over with the shouting. The double integral is a iterated integral, and then fundamental theorem and a bunch of elbow grease, and I can compute that iterated integral to get an answer. Everybody all right? Okay, it's a good stopping point. Y'all have a great weekend. See you later. See you on Monday. Don't forget to come talk to me if you didn't get marked down yet for attendance.